How 3IATLAS challenges science. For centuries, humanity believed it understood the basic rules of the cosmic neighborhood. Our solar system was thought to be a close family, planets born from the same disk of dust, comets shaped by our sun, asteroids left over from planetary formation. Everything we observed we assumed belonged to us. Then came 3IATLAS, not with noise, not with fireworks, but with quiet defiance. When astronomers first detected this object, it appeared ordinary, just another faint traveler crossing the darkness. But as data accumulated, something felt wrong. Its trajectory did not bow politely to expectations. Its speed did not match solar system norms. Its origin did not trace back to the familiar Oort cloud or Kuiper belt. This was not just another rock. This was a visitor. And visitors change everything. In science, revolutions rarely announce themselves loudly. They slip in through anomalies, small inconsistencies that refuse to disappear. 3IATLAS was one such inconsistency, but on a cosmic scale. It did not behave like comets we had cataloged for decades. It did not follow the gravitational handwriting we had learned to read. It was as if the universe had dropped a question mark into our equations. Michio Kaku often reminds us that science advances not by confirming what we know, but by confronting what we don't. 3IATLAS does exactly that. It challenges the comforting idea that our solar system is typical. It forces us to confront a far more unsettling possibility that the universe is not only vast, but active, dynamic, and constantly exchanging material across star systems. Interstellar objects were once theoretical. Elegant equations suggested their existence, but theory is cheap in physics. Evidence is expensive. 3IATLAS is evidence. This object did not form here. Its atoms were forged around another star, possibly billions of years older than our sun. Its chemical memory carries information from a distant planetary system, perhaps one that no longer exists. In that sense, 3IATLAS is not merely an object, it is a messenger. And messages make scientists uncomfortable, because messages imply context. To accept 3IATLAS is to accept that planetary systems leak, that stars do not keep their creations to themselves, that the Milky Way is less like a collection of isolated islands and more like a vast ocean, where debris, matter, and possibly even precursors of life drift freely between stellar shores. This immediately challenges a foundational assumption in astronomy that planetary evolution is largely local. If interstellar objects are common, and 3IATLAS suggests they might be, then every solar system is shaped not only by its own history, but by the leftovers of others. That changes models, that changes simulations, that changes textbooks. But the challenge goes deeper. 3IATLAS also forces us to re-examine how we detect reality. For decades, our telescopes were blind to such objects, not because they were rare, but because our instruments were not designed to see them. This raises a disturbing question. How many cosmic truths have passed through our neighborhood unnoticed? Science prides itself on objectivity, yet it is limited by tools, assumptions, and expectations. 3IATLAS exposes those limits. It reminds us that the universe does not care what we are prepared to observe. In Kaku's language, this is the universe whispering, "Your theories are provisional." And then there is the speed. 3IATLAS moved too fast to be comfortably explained by standard gravitational capture. Its velocity hinted at an origin far beyond nearby stars. Some calculations suggest it may have wandered the galaxy for millions, perhaps billions, of years before briefly intersecting our sun's domain. Imagine that. While Earth was forming continents, while life was crawling out of oceans, while civilizations were rising and falling, this object was traveling. That alone reframes our sense of time. Human history collapses into irrelevance when measured against interstellar journeys. 3IATLAS is older than nations, older than languages, possibly older than life itself. Science is not threatened by such realizations, but human ego is. Another challenge lies in composition. Preliminary spectral analysis hints at materials not commonly seen in solar system bodies. If confirmed, this would mean that planetary chemistry varies more widely than expected. The building blocks of worlds may differ dramatically from system to system. And if chemistry varies, then biology might too. This is where science becomes philosophy. Because 3IATLAS subtly undermines the assumption that Earth-like conditions are the default template for life. If interstellar material routinely crosses star systems, then panspermia, once considered fringe speculation, re-enters serious scientific discussion, not as belief, but as possibility. Michio Kaku often says that today's science fiction is tomorrow's science fact. 3IATLAS occupies that boundary zone. It does not prove life beyond Earth, but it weakens the argument against it. And perhaps the most uncomfortable challenge of all is psychological. Science likes control. Predictability, repeatability. Interstellar visitors introduce randomness. They arrive uninvited, they do not stay long, they leave more questions than answers. 3IATLAS reminds us that the universe is not a closed laboratory experiment. It is an open system, messy and unpredictable. Our solar system is not isolated, it is exposed. That realization forces a paradigm shift. not just in astronomy, but in how we think about our place in the cosmos. We are not observers standing outside the universe. We are participants moving through it. And 3IATLAS is proof. This is only the beginning, because if one interstellar object can challenge centuries of assumptions, what happens when we detect hundreds, thousands? What happens when we learn to track them before they pass us by? The age of isolated astronomy is ending. The age of galactic science has begun. When scientists accepted that 3IATLAS did not belong to our solar system, they unknowingly crossed an invisible boundary in scientific thinking. Until now, interstellar space was treated as an abstract background, a dark, empty stage upon which stars performed. But 3IATLAS transformed that background into an active highway. This was no longer about one object. This was about traffic. The universe, it turns out, is not still. For decades, astronomical models assumed that matter formed around stars, evolved locally, and remained gravitationally loyal to its birthplace. Interstellar escape was considered rare, inefficient, almost negligible. 3IATLAS directly contradicts that assumption. Its very existence implies that stars routinely eject material with enough energy to escape their gravitational grip. That changes stellar physics. If stars frequently fling debris into deep space, then planetary systems are far more violent than we imagined. Collisions, near misses, gravitational slingshots, these are not exceptions but standard features of planetary evolution. 3IATLAS may be the fossilized scar of such an ancient catastrophe. Somewhere, around some distant star, a world may have shattered, and we are witnessing the debris. This realization reframes destruction itself as a creative force. In the universe, nothing is truly lost. Matter is recycled, redistributed, repurposed. 3IATLAS is recycled history, drifting through the Milky Way like a cosmic memory fragment. Michio Kaku often speaks about the universe as a system governed by elegant laws, yet capable of immense chaos. 3IATLAS sits at the intersection of elegance and chaos. Its motion obeys physics precisely, yet its origin story is wildly unpredictable. This creates a problem for simulation-based science. Modern astrophysics relies heavily on computer models. We simulate star formation, planetary disks, and long-term orbital stability. But these simulations rarely include large-scale interstellar exchange of solid bodies. Why? Because until recently, there was no evidence forcing us to. Now there is. To incorporate 3IATLAS properly, scientists must rebuild models from the ground up, not tweak them, not patch them, rebuild them. And rebuilding science is never comfortable. Another challenge lies in detection bias. 3IATLAS was found not because we expected it, but because our technology accidentally became good enough. This implies a disturbing truth. The universe may be filled with interstellar objects, yet our awareness of them is only beginning. In other words, reality did not change. Our perception did. This echoes a recurring theme in the history of science. When Galileo pointed his telescope at the sky, the universe did not suddenly gain moons around Jupiter. They were always there. Humanity simply lacked the tools to notice. 3IATLAS is our Galileo moment for interstellar space. And just as Galileo's discoveries shattered Earth-centered cosmology, 3IATLAS threatens sun-centered thinking. The solar system is no longer the primary frame of reference. It is merely one node in a galactic network. This forces astronomers to adopt a Milky Way scale mindset. Questions now shift dramatically. How many interstellar objects pass through the solar system each year? How many collide with planets? How many carry complex organic chemistry? How many pass through habitable zones elsewhere? Each question destabilizes long-held assumptions. Perhaps the most unsettling implication is frequency. If 3IATLAS is not rare, then Earth has likely been bombarded by interstellar material throughout its history. Some of that material may have arrived during the early stages of life. This is not speculation, it is statistical logic. And statistical logic is dangerous because it does not require certainty, only probability. Science once treated panspermia, the idea that life's ingredients travel between stars, as fringe thinking. But 3IATLAS drags that idea out of the shadows and places it on the laboratory table. Not as belief, not as faith, but as hypothesis, and hypotheses demand testing. But how do you test an object that refuses to stay? 3IATLAS is fast. It does not linger. It does not orbit. It enters, it passes, it leaves. This creates a logistical nightmare. Our spacecraft are slow compared to interstellar visitors. By the time we detect them, they are already on their way out. This exposes a technological gap. Humanity is a species capable of detecting cosmic anomalies, yet largely incapable of intercepting them. This gap challenges not just astronomy, but space policy, engineering priorities, and long-term planning. If interstellar objects carry priceless scientific information, then missing them is not neutral. It is a loss. Michio Kaku frequently emphasizes that scientific revolutions are followed by technological revolutions. 3IATLAS may force humanity to develop rapid response space missions, autonomous probes, and AI-driven detection systems designed specifically for interstellar interception. In that sense, this object is not just challenging science, it is directing its future. There is also a philosophical discomfort embedded here. Science prefers reproducibility, but interstellar visitors are one-time events. Each is unique. Each carries a different history. This pushes science toward a more historical, forensic mode of thinking. We are no longer just predicting outcomes, we are reconstructing stories. 3IATLAS is a story fragment without a beginning or an ending. It enters the middle of our narrative and leaves before we can ask it questions. That frustrates scientists because it resists closure. And yet, that is precisely why it matters. The universe is not obligated to provide neat data sets. Another challenge emerges when we consider scale. Interstellar objects operate on timescales far beyond human planning. 3IATLAS may have traveled longer than our species has existed. Its journey mocks our short-term thinking. Civilizations plan in decades. Galaxies evolve in billions of years. 3IATLAS belongs to the galaxy's clock, not ours. To study such objects properly, science must adopt patience as a methodology. Long-term observation programs, generational research agendas, and continuity of knowledge become essential. This clashes with modern scientific culture, which often prioritizes fast results and short funding cycles. In this way, 3IATLAS challenges not just theories but institutions. It forces us to ask uncomfortable questions about how science is organized, funded, and prioritized. Are we prepared to study phenomena that do not align with human attention spans? Because the universe clearly does not care. And then there is humility. 3IATLAS humbles us by reminding us that we are latecomers. The cosmos was active long before humans learned to look up. Interstellar objects have been passing through this region of space long before Earth had oceans. We are not witnessing a new phenomenon. We are witnessing our first awareness of it. That distinction matters. Science often mistakes discovery for creation. 3IATLAS corrects that arrogance. It tells us that reality is always ahead of our understanding. And this is precisely why it challenges science so profoundly. Because it does not fit neatly into existing categories. Because it forces new questions faster than answers. Because it exposes blind spots in our tools and thinking. Because it reminds us that the universe is larger, older, and stranger than our models suggest. And this is still only the surface. Because once we ask where 3IATLAS came from, the next inevitable question is far more unsettling. What else is out there, moving silently between the stars that we have not yet learned to see? As scientists began to accept the implications of 3IATLAS, a deeper unease settled in. The discomfort was no longer limited to astronomy. It spread into physics, chemistry, planetary science, and even the philosophy of knowledge itself. This object was not just challenging what we know, it was challenging how we know. At the heart of the issue lies a silent assumption science rarely questions. That the universe is statistically smooth, that most systems behave like averages, that outliers are rare and ignorable. 3IATLAS refuses to be ignored. It is an outlier with consequences. In traditional planetary science, objects are categorized neatly. Comets have icy signatures. Asteroids are rocky. Kuiper belt objects sit quietly at the edges of solar systems. 3IATLAS fits none of these categories perfectly. Its physical behavior appears ambiguous, its spectral signals unclear, its structure unresolved. This ambiguity is not a flaw in the object. It is a flaw in our classification system. Science loves labels because labels give the illusion of understanding. But when something cannot be labeled, it exposes the fragility of our frameworks. 3IATLAS forces scientists to confront an uncomfortable truth. Nature does not care about our categories. Michio Kaku often explains that every major scientific breakthrough occurs when existing frameworks collapse under the weight of new data. Newtonian physics collapsed into relativity. Classical mechanics gave way to quantum uncertainty. In the same way, solar system-centric thinking is now collapsing into galactic thinking. This transition is not smooth. One of the most profound challenges introduced by 3IATLAS is uncertainty. Its brief appearance leaves large gaps in data. Its trajectory is well measured, but its internal structure remains unknown. Is it solid, porous, composite, fragmented? Each possibility leads to a different origin story. And origin stories matter because they determine how we model planetary formation across the galaxy. If 3IATLAS is porous, it suggests gentle aggregation in cold environments. If it is dense, it implies violent compression and collision. If it is layered, it suggests complex geological history on a body that never belonged to our sun. This turns planetary science inside out. We are used to studying planets by observing them over long periods. We map surfaces, measure atmospheres, track seasonal changes. Interstellar objects deny us that luxury. They appear suddenly, vanish quickly, and leave us with incomplete clues. This forces science into a detective role. And detective science is probabilistic, not definitive. That shift is deeply uncomfortable for a discipline built on reproducibility. Another challenge emerges when considering motion. 3IATLAS does not orbit the sun, it does not return, it does not repeat. Its path is a one-time crossing, a hyperbolic trajectory that will never be retraced. This breaks a foundational assumption in celestial mechanics: predictability through repetition. Planets return, comets return, asteroids return. Interstellar objects do not. They introduce irreversibility into a system that once felt clockwork perfect. This aligns more closely with thermodynamics than classical astronomy. The solar system becomes an open system subject to external perturbations. This has consequences. Long-term orbital stability models may need revision. The probability of random impacts from interstellar debris must be reconsidered. Even the history of mass extinctions on Earth may require an examination through a galactic lens. Not because interstellar objects caused them, but because they could have. This is where science becomes unsettling, because it forces us to acknowledge that our planet's history may have been shaped by events originating far beyond the Sun. Earth is not isolated from the galaxy's violence. It is embedded within it. 3IATLAS also challenges our understanding of material endurance. To survive interstellar travel for millions of years, an object must withstand radiation, temperature extremes, and collisions with interstellar dust. This implies material properties more robust than many solar system bodies. What kind of world produces such debris? Perhaps one with stronger gravity. Perhaps one orbiting a more active star. Perhaps one that no longer exists. This turns 3IATLAS into a relic, possibly the last surviving fragment of a destroyed planetary system. In that sense, it is less like an asteroid and more like a cosmic fossil. Fossils tell stories, but only if we know how to read them. Another challenge lies in scale mismatch. Human science operates on laboratory scales. We test materials in chambers, simulate impacts in accelerators, recreate conditions in controlled environments. But 3IATLAS represents conditions that cannot be replicated. Its journey itself is the experiment. This forces science to rely on inference rather than control. We must infer composition from reflected light, internal structure from motion, history from statistical context. Each inference carries uncertainty, and uncertainty accumulates. This accumulation does not weaken science, it matures it. It pushes science away from absolutism and toward humility. But humility is a cultural shift, not just an intellectual one. Michio Kaku often emphasizes that the universe is under no obligation to be simple. 3IATLAS embodies that statement. It is simple in appearance, yet complex in implication. A small object causing large conceptual ripples. Perhaps the most destabilizing challenge introduced by 3IATLAS is that it hints at hidden populations. If one interstellar object has been detected, logic dictates many more exist. Some smaller, some faster, some undetectable with current technology. This introduces the idea that our cosmic census is radically incomplete. And incomplete knowledge is dangerous, not because it is wrong, but because it breeds false confidence. For centuries, humanity believed the night sky was static. Then we discovered galaxies, then expansion, then dark matter, then dark energy. Each discovery revealed that what we see is only a fraction of what exists. 3IATLAS fits perfectly into this historical pattern. It is another reminder that the visible universe is not the whole universe. And this realization brings us to a deeper philosophical challenge: meaning. Science seeks patterns, laws, and explanations. But interstellar objects operate at the edge of statistical predictability. Each one is unique. Each one carries a different past. They resist generalization. This forces science to balance two opposing needs: the need for universal laws, the need to respect singular events. 3IATLAS sits in that tension. It obeys gravity, yet defies expectation. It follows physics, yet challenges theory. And in doing so, it exposes the limits of reductionism, the idea that understanding parts automatically explains the whole. The universe, it seems, is not just a machine. It is a history. And 3IATLAS is a page torn from a book we have not yet learned to read. This is why it challenges science so deeply. Not because it breaks laws, but because it reveals how incomplete our questions have been. And as long as interstellar visitors continue to pass through unseen, science will remain a work in progress. By the time scientists reached part 4 of their intellectual confrontation with 3IATLAS, a quiet realization emerged. This object was not merely challenging existing theories, it was reshaping the direction of future science. The questions it raised could not be answered with current tools, current timelines, or current priorities. This is how scientific revolutions begin, not with answers, but with questions that refuse to stay small. One of the most profound challenges posed by 3IATLAS lies in measurement itself. Science depends on precision. We trust numbers because they feel solid, objective, reliable. But interstellar objects move fast, fade quickly, and offer only brief windows of observation. This compresses years of data collection into weeks or days. Precision under pressure becomes fragile. Tiny errors in velocity estimation can translate into massive uncertainties in origin tracing. When scientists attempt to rewind the path of 3IATLAS backward through the galaxy, they are forced to confront a chaotic gravitational environment. Stars move. Spiral arms rotate. Molecular clouds drift. The galaxy is not a static map, it is a moving storm. Tracing the birthplace of 3IATLAS is therefore not like following a straight line backward. It is like reconstructing a path through a hurricane long after it has passed. This introduces probabilistic thinking at a scale rarely seen in astronomy. Science must now embrace galactic chaos as a standard condition. This challenges the deeply rooted assumption that astrophysical systems can always be approximated as stable over long timescales. Stability, it turns out, is local and temporary. On galactic scales, randomness dominates. Michio Kaku often describes the universe as a symphony governed by equations, but even symphonies have improvisations. 3IATLAS represents an improvisation the score did not anticipate. Another challenge emerges when considering energy. To escape a star system, an object must acquire immense kinetic energy. This energy does not appear spontaneously. It must come from gravitational interactions, often violent ones. This implies that planetary systems routinely experience extreme events: closed stellar flybys, giant planet migrations, chaotic orbital rearrangements. 3IATLAS is indirect evidence that planetary systems are not quiet nurseries, they are turbulent arenas. This realization challenges the romanticized image of slow, orderly planetary formation. Instead, the universe builds worlds through disruption. This insight forces scientists to rethink habitability models. Traditional models assume long-term stability as a prerequisite for life. But if planetary systems are frequently disturbed, then life must either be incredibly resilient or incredibly rare. Both possibilities are unsettling. 3IATLAS does not answer this question, but it sharpens it. It forces astrobiology to confront a harsher universe, one where stability is earned, not guaranteed. Another deeply uncomfortable challenge arises from selection bias. The interstellar object we detected is the one that happened to pass close enough and bright enough to be seen. This implies that countless others passed unnoticed. This creates a distorted sample. Imagine judging an entire ocean by the few fish that jump above the surface. That is effectively what current astronomy has been doing. 3IATLAS is not representative, it is merely detectable. This undermines confidence in population estimates. How many interstellar objects are out there? How big are they? How fast do they move? How often do they intersect planetary systems? Science cannot yet answer these questions, and that ignorance is now explicit. 3IATLAS forces scientists to publicly acknowledge uncertainty, cultural shift in a field that often prefers confident projections. Michio Kaku frequently emphasizes that admitting ignorance is not weakness, it is the engine of progress. 3IATLAS forces that admission. There is also a challenge to observational strategy. Traditional astronomy focuses on fixed target stars, nebulae, galaxies. Interstellar objects demand a shift toward event-based astronomy, a mode of observation that prioritizes transient, unpredictable phenomena. This aligns with a broader transformation already underway. Gravitational waves, fast radio bursts, gamma-ray bursts, all are fleeting signals. 3IATLAS joins this category, reinforcing the idea that the universe reveals itself in moments, not constants. Science must become faster, more adaptive, more autonomous. Human reaction times are no longer sufficient. Detection, classification, and response must increasingly be handled by artificial intelligence. In this sense, 3IATLAS is indirectly accelerating the integration of AI into scientific discovery. The object challenges not only what we study, but how we study. Another layer of challenge appears when considering contamination. If interstellar objects routinely pass through planetary systems, they may exchange material with planets, either through impacts or atmospheric interactions. This complicates planetary protection frameworks. For decades, space agencies worried about contaminating Mars with Earth microbes. 3IATLAS introduces the inverse problem: Earth may already have been contaminated by the galaxy. This does not imply danger, but it implies connectivity. Life, if it exists elsewhere, may not be neatly separated by star systems. The galaxy could function as a slow, inefficient, but persistent mixing chamber. This idea destabilizes the concept of independent origins of life. It suggests that biology may be a galactic phenomenon, not a planetary one. That idea alone challenges the boundaries between astronomy, biology, and chemistry. Science prefers disciplines. The universe prefers integration. 3IATLAS sits at the crossroads of multiple fields, forcing collaboration where silos once existed. Planetary scientists must talk to astrobiologists. Chemists must talk to dynamicists. Astronomers must think like historians. This is intellectually demanding, and demanding science often meets resistance. Some will argue that 3IATLAS is an anomaly, not a revolution. That it is interesting, but not transformative. History suggests otherwise. Anomalies ignored become revolutions delayed. Copernicus was an anomaly. Quantum mechanics was an anomaly. Dark energy was an anomaly. 3IATLAS carries the same signature, not because it is large, not because it is mysterious, but because it refuses to fit comfortably into existing narratives. And science advances by rewriting narratives. Perhaps the deepest challenge of all is existential. 3IATLAS reminds us that Earth is not protected by isolation. We are embedded in a galaxy that moves, collides, exchanges, and evolves. Our planet is not a sanctuary outside cosmic history. It is part of it. This realization dissolves the boundary between air and out there. The stars are not distant abstractions. They are neighbors, capable of sending fragments of their past directly through our skies. 3IATLAS is one such fragment, and it is telling us something important. The universe is not finished surprising us. At this stage, the challenge posed by 3IATLAS evolves from interpretation to preparation. Science is no longer asking only what does this mean. It is now asking a far more urgent question: are we ready for the next one? Because 3IATLAS is not the last interstellar visitor. It is the first clearly recognized member of a much larger population. This realization transforms interstellar objects from curiosities into a category, one that science must now plan for. Planning is where theories collide with reality. The current astronomical infrastructure was not designed for this. Telescopes scan the sky in predictable patterns. Observation schedules are planned months in advance. Funding cycles assume slow, incremental progress. Interstellar objects violate all of these assumptions. They arrive without warning, they move quickly, they disappear forever. This forces a fundamental redesign of scientific priorities. Michio Kaku often points out that future science will be driven not by individual discoveries, but by platform systems capable of adapting in real time. 3IATLAS demands exactly that. It is pushing astronomy toward a surveillance model of the sky, where continuous monitoring replaces targeted observation. This is not just a technical shift, it is a philosophical one. Science has long focused on static truths. Interstellar objects require dynamic thinking. Knowledge must update continuously, incorporating incomplete data and probabilistic predictions. This blurs the line between discovery and decision-making. Another deep challenge arises from chemistry. Preliminary analysis suggests that interstellar objects may carry compounds unfamiliar to solar system chemistry. These compounds formed under different radiation environments, different elemental ratios, and different thermal histories. This means chemistry itself may be context-dependent on a galactic scale. If confirmed, this would destabilize a long-held assumption that chemistry is universal in practice, even if universal in law. The laws may be the same, but the outcomes may vary dramatically. This has consequences for astrobiology. Life as we know it is built on a narrow subset of chemical possibilities. But 3IATLAS hints that nature experiments far more freely than Earth-based biology suggests. The building blocks of life elsewhere may follow unfamiliar pathways. This does not mean life is common, it means life may be strange, and strange life challenges detection strategies. Most searches for extraterrestrial life are biased toward Earth, like signals, oxygen-rich atmospheres, water signatures, familiar organic molecules. Interstellar objects remind us that life may not announce itself in recognizable ways. Science may be looking for mirrors, when it should be looking for shadows. Another challenge lies in trajectory prediction. Interstellar objects do not follow tidy, circular orbits. Their paths are influenced by the gravitational tapestry of the galaxy. Each star cloud and cluster subtly alters their motion. This introduces long-term unpredictability. In classical astronomy, unpredictability was an inconvenience. In galactic astronomy, it becomes the norm. This pushes science closer to chaos theory, where small uncertainties grow over time. 3IATLAS demonstrates that the galaxy is not a clean system. It is sensitive, interconnected, and nonlinear. This has implications beyond astronomy. If unpredictability is fundamental, then future technologies, interstellar probes, navigation systems, even hypothetical starships, must be designed to operate under uncertainty. Precision will give way to adaptability. 3IATLAS is quietly training humanity for a more complex universe. Another challenge emerges when considering scale of responsibility. If interstellar objects can impact planets, then planetary defense is no longer a local problem. It becomes a galactic risk assessment. Asteroid defense strategies currently focus on solar system objects with predictable orbits. Interstellar objects invalidate those strategies. They are faster, harder to detect, and less predictable. This forces a reevaluation of what it means to protect the planet. Science, policy, and ethics begin to overlap. How much should humanity invest in detecting rare but potentially catastrophic events? How do we balance probability against consequence? 3IATLAS does not answer these questions, but it forces them into the conversation. Michio Kaku often emphasizes that advanced civilizations survive by anticipating threats, not reacting to them. Interstellar objects represent a class of threat that cannot be negotiated with, reasoned with, or prevented, only anticipated. This is an uncomfortable lesson. Another profound challenge arises from the idea of galactic archaeology. If interstellar objects are fragments of destroyed worlds, then each one is a data capsule from a lost system. Studying them could reveal how common planetary destruction is in the galaxy. This reframes catastrophe as data. Destruction is no longer just tragedy, it is information. This forces science to confront uncomfortable moral intuitions. We are learning from the ruins of worlds that may once have been habitable, possibly even inhabited. The silence of the galaxy may not mean emptiness, it may mean aftermath. 3IATLAS does not confirm this, but it opens the door to the question. And once opened, that door cannot be closed. Another challenge lies in public perception. Interstellar objects capture imagination. They trigger speculation, fear, and excitement. Science must communicate carefully, balancing honesty with restraint. Overhyping leads to distrust. Understating leads to apathy. 3IATLAS tests science's ability to speak responsibly about uncertainty. This is not trivial. Public trust is part of scientific infrastructure. Without it, even the best data loses impact. Finally, 3IATLAS challenges humanity's sense of future. It reminds us that our planet exists in a dynamic galaxy, shaped by forces beyond local control. Our long-term survival may depend on understanding those forces, not mastering them, understanding them. This shifts the narrative from dominance to coexistence. We are not rulers of the cosmos. We are residents, and residents must learn their neighborhood. 3IATLAS is a first map fragment of that neighborhood, incomplete, cryptic, but invaluable. The question now is not whether science will change. It already has. The question is whether humanity will change with it. With 3IATLAS, science is forced to confront a question it usually avoids unless absolutely necessary: intelligence. Not because this object shows signs of design, but because its existence expands the stage upon which intelligence, anywhere in the galaxy, might operate. This distinction matters. Science does not begin with speculation. It begins with implications. And the implications of 3IATLAS quietly extend beyond rocks and trajectories into the realm of possibility. If interstellar objects are common, then civilizations, should they exist, are not confined to their home star systems in the way we once assumed. Material exchange across the galaxy becomes not just possible, but inevitable. This does not imply intention, it implies opportunity. A civilization does not need faster than light travel to influence distant regions of the galaxy. It only needs patience. Objects like 3IATLAS demonstrate that the galaxy itself provides a natural transport mechanism. Matter drifts, debris travels. Time does the rest. From a cosmic perspective, millions of years are not long. This reframes intelligence as something that might operate on geological and galactic timescales, not human ones. Science has historically searched for signals, radio waves, lasers, bursts of energy. 3IATLAS hints that influence might also be physical, subtle, and slow. This challenges Sati's-style thinking. What if intelligence leaves artifacts not meant to communicate, but simply to persist? What if traces of advanced activity are embedded in debris indistinguishable from natural objects, unless one knows how to look? Science must tread carefully here. 3IATLAS provides no evidence of artificial origin, none. But it does expose a blind spot. Our search strategies are shaped by human expectations of communication. The universe may not share those expectations. Michio Kaku often emphasizes that advanced intelligence may appear indistinguishable from nature itself. Not because it hides, but because it operates at scales and efficiencies beyond our intuition. 3IATLAS forces science to consider this without abandoning rigor. Another challenge lies in information preservation. Interstellar space is a harsh environment. Radiation erodes surfaces, collisions abrade structure, yet 3IATLAS survive. This implies that information, chemical, structural, isotopic, can persist across vast distances and times. The galaxy is not a perfect eraser, it is a low-resolution archive. This transforms interstellar objects into potential time capsules. Not intentional ones, natural ones. But natural archives can still be read. Isotopic ratios can reveal stellar ancestry. Molecular composition can reveal formation environments. Structural integrity can hint at internal history. 3IATLAS carries all of this silently. Science is now confronted with a new discipline: interstellar forensics. This discipline operates without crime scenes, without witnesses, without repetition. Each object is unique. Each tells a partial story. Science must reconstruct the past using fragments scattered across space. This is intellectually demanding and deeply humbling.